Another example of subspaces are going to be spanning sets. Any spanning set is always a subspace. So if we have a certain vector space V and we have certain vectors inside of V, let's say U1, Un, so the space that they span, so this is always a subspace of V. So these vectors can be vectors in Rn if the space is for n, but as I said before, they can be also vectors in any other space. So they can be, for instance, polynomials, they can be matrices, can be elements in any space. So, for instance, in the space, the vector space R2, we have that the span of the vectors 1, 0, 0, 1, we know that this is the whole R2, right? I mean, these two vectors span the whole R2. So what is the space that span the vectors, for instance, 3, 1, 1, 1? Well, we can calculate also what is the space that these vectors span. We know that these ones, we know right away that span R2 because it's the standard base, right? So we know that that will span R2 in the same way that we know that the span of the vectors 1, 0, this is R3. And we know also that the polynomials, just the number 1, polynomials degree 0, the polynomial x, just a polynomial with one term, equal x, the polynomial x squared, the polynomial x cubed, until the polynomial xn. So these vectors span the space polynomials of degree less or equal than n. And we know that the space spanned by these matrices is the whole spaces of matrix 2 by 2. So these are like the spaces that we know already what they span, because these are like the standard unit bases. We can see clearly how any matrix of 2 by 2 can be written as a combination of these four matrices. But the bases are not unique. It must be that the same space is also spanned by other matrices. For instance, the question is the spanning set here equal to R2? I mean, any vector of R2 can be actually written as a combination of these two. Well, we know already how to do that, right? So the question is, any xy can be written as A times 1, 2 plus B times 3, 1. So that will be the question. And for that to be true, x have to be equal to A plus 3B, and y have to be equal to 2A plus B. So this is a system of equations whose matrix is 1, 3, 2, 1, and the augmented matrix is x, y, right? Since these are the values in the other side of the equal sign. And so, in order to know if this system is consistent or not, because that is what we need in order to know if it's going to have solution for that, right? So we need to know if the system is consistent. So remember that for square matrices, we have the result that the determinant of A is not 0 is completely equivalent to the system AX equal B is consistent for all B. That's the part that is relevant here. So if the matrix is square, since the matrix is m by n, we know that the system AX equal B, I mean putting here anything, in other words, so the system AX equal B is consistent for all B only in case that the determinant of the matrix, I mean the determinant of the matrix of the system is not zero. So in this case, it's very easy to check then if this system has a solution or not. Let's just calculate this determinant, 1, 3, 2, 1. So let's calculate this determinant. This is 1 minus 6, that is not 0. And so because of that, we know that this system is going to be consistent because all the systems are, right? I mean, for any B that you put here. So this system is consistent for all x, y that you will put here. So what means is that no matter what point in R2 is, any point can be written as a combination of these two. We can say then that this is true, right? So the spanning set here is the whole R2. So let's see another example. Same question. Is the set here spanning by this the whole R2 with these other two vectors? Well, we need to do the same. I mean, essentially, we need to form the system as we did before, that in this case will be just 1 minus 2 minus 2, 4, right? So this is the determinant that we are interested in. So this determinant, so this will be just doing like that, that will be 4 minus 4 is 0. And so because of that, applying the same result as before, we can say that the system is not consistent for all xy. So meaning that it will exist some xy here that is not possible to write it as a combination of these two. So the answer to this question is the set spanned R2. No, in this case it's not R2 because are going to be some xy in R2, right, that cannot be written as a combination of these two. Let's see how we do the same thing now, but with these less familiar vectors. I mean, a subspace of P2. I mean, the subspace of polynomials of degree less or equal than 2. So let's consider these three vectors. The vector 1 minus x. I mean, now vectors are polynomials, right? Because the polynomials are the elements in P2. So the question is the span of this polynomial, and this other polynomial. I mean, these three vectors, or these three polynomials, do they span the whole set P2? I mean, the whole set of polynomials of degree 2? Well, the idea will be, let's write down a polynomial of degree 2. ax squared plus bx plus c. That will be a generic polynomial of degree less or equal than 2. So when we put here any a, any b, and any c, we obtain a polynomial of degree less or equal than 2. So for instance, if we put 0, 1, 1, we obtain the polynomial x plus 1, which is a polynomial of degree less than 2. Okay, so any polynomial of degree less or equal than 2 is going to be written in this way. The question now is it any polynomial being able to be written as a combination of these two, meaning a number? I use already a b, c here for the coefficients. Let me put a number like k1. A number times this one plus another number times the other one plus another number times the other one. Let's write it like this, so we see clear that are the three polynomials that are written here, and I'm introducing three variables, right? K1, K2, K3. So the question will be, do these K1, K2, K3 exist always for all A, B, and C? So let's do the operations. So let's do the operation that in this case will be just multiplication of polynomials. This is K1 minus K1x Okay, and now we combine like terms. In degree 2, we have only this one. In degree x, we have this 2x cubed minus k1. 2k3 minus k1. And in numbers, we have only this one, will be plus k1. So what we have is that a generic polynomial like this written in this way. So for that to happen, a should be equal to k2. And b should be equal to all this, 2k3 minus k1. And c should be equal to just k1. Okay, we can write this as we will normally do with polynomials, putting in order k1, k2, k3. So the first equation will be k2 equals a. The second one will be minus k1 plus 2k3 equals b. And the third one will be just k1 equal c. So this is the system that we will study the matrix associated. So the matrix associated to this system is 0, 1, 0, and then minus 1, 0, 2, and then 1, 0, 0. And so the column here will be ABC, right? So the thing is that here we are talking about any ABC. The question is, does this system have solutions for all ABC? Okay, as this is still a square matrix, we just calculate the determinant of this matrix. We can expand it, for instance, for this row, and this will be plus minus plus, so will be just 1 times this determinant here, and this determinant is 2. So the determinant of this matrix is 2. So since this determinant is not 0, this system here is then consistent for all ABC, no matter what we put there. So that means then that the original question, does this thing span the whole P2? Yes, so any vector that is a polynomial of degree less or equal than 2 will be spanned by these 3 polynomials. Moreover, if you want to consider a concrete polynomial, any polynomial of degree less or equal than 3, this system will give you the formula to find out which ones are really the coefficients that you need to put here, k1, k2, and k3. So for instance, let's just consider a polynomial here of degree less or equal than 2. So any polynomial of degree less or equal than 2, let's say for instance 3x squared minus 5. So how 3x squared minus 5 can be written as a combination of these 3 vectors? Well, this system of equations here tell us how. So we need to put just the coefficients of whatever polynomial we want here. So in this case, the coefficients of this polynomial will be 3, 0, minus 5. So our system will be just the same, but here we are going to put these numbers, 3, 0, minus 5. And so as we know that this was consistent for all ABC, it's going to be consistent in particular for this one. And so from here we can find directly the solution. Well, we have the solution of k1 and k2 directly, and from here we get that k3 is equal to k1 divided by 2. So k3 is equal to k1, which is minus 5 over 2. Here is k3. So what is then the combination that gives this vector? I mean, what is this combination here? So will be k1, that in this case we obtain that is minus 5. So will be minus 5 times the first vector, which is 1 minus x, plus k2, which is 3, times the second vector, which is x squared, and plus k3, which is minus 5 over 2 times the third vector, which is 2x. So you can check that this combination will really give this polynomial. But then we prove that the space spanned by these polynomials is the whole subspace of polynomials of degree less or equal than 2.